Hello everyone. So now in this video we are going to look on into the finite automata, basics of finite automata, the formal definition of this, what are the types of finite automata, and how to convert from a regular expression to finite automata with examples, and that defines for DFA and NFA. So let's go on into the video and see how the finite automata works here for the compiler. Yes. Here we'll have a small recap on the regular expression. I told you that is a set of strings forms the language which defines the rules or the patterns to be matched for the input string. Now let's go on into the finite automata. Here, before understanding technically what is a finite automata, I'll give you a short real-time example in order to understand what is a state diagram. So here we have a sample state diagram for a simple soda vending machine. So we all aware of soda vending machine. It transits from one state to another state. It will not be in a same idle state. So initially it will be in idle state, and when the user comes and puts the coin, it enters from idle state into the count state. So now if the vending machine starts counting the coins, if the coins are sufficient, it will either move to the next state, or if the coins are not enough, it will be waiting in the same state. Likewise, when the coin count is matched, it will dispense the required product by the user, and it will go again back to the idle state. So these are all the states prevailing in the vending machine working condition. Similarly, if we want to make the compiler to work in real time, it reads the input from the user through the program, and it has to check whether the input is matching with the pattern or the regular expression, and it is given in a format as a token. We have to segregate the given input as a token in terms of keywords, identifiers, constants, punctuation symbols, operators, and in kind of. So now we'll see what is a finite state automata in a example with a formal definition. So here comes the finite state automata. The finite state automata is the very basic and important for the lexical analyzer of the compiler, which is the first phase of the compilation. Using the formal definition, this finite automata can be defined as a tuple that consists of 5 symbols. Those symbols are called as the first one Q, which is called as the set of state. As we saw in the previous example, we had several states marked as an oval shape. So everywhere the finite automata must consist of a set of states. Then sigma, that consists of set of symbols. So whenever a regular expression is written, definitely there must be input symbols through which the expression or the pattern can be defined. So the second one is the set of symbols. Third one is the initial state and final state. Always a machine will start from the initial and it will end at somewhere in the state. So we have to provide one starting state, otherwise termed as initial state, and one final state. And there is no restriction, we should end only in one final state. We can have n number of final states. So that is why it is termed as set of final states. And the very important thing of a FSA or a finite automata is the transitions. So the transition, or where it provides the change from one state to other state based on the input symbol. So those transitions are called as depicted at the last set in the tuple. So this is the formal definition of the finite state automata, and it is diagrammatically denoted at the right hand side, where we are taking the input symbols, and the automata is designed which consists of several states, and below which the output is generated whether it is matched with the pattern or not. Okay, so now let's see how the regular expression is being now converted into finite automata. So we have seen the introduction to regular expression in the previous video, and we are going to take that input and let's see how the finite automata can be generated. So in the first example, where it is given as a plus b, using the property of regular expression, it can be called as a union b. It means that a can occur or b can occur. So we are giving one start state as Q1 and one final state Q2. This is basic thing. And here the transition is termed as A can occur or B can occur. That is why the transition is depicted in green color arrow mark, on which we are going to mark it as A comma B. A comma B states that either A can occur or B can occur. In the second case, the AB is called as the concatenation of AB, which means that B must follow A. So that means now we are having the starting state Q1. From Q1, we are transiting to the state Q2 on input symbol A. From Q2 on input symbol B, we are leading to Q3, which is the final state. And to depict the A star, here the A should be taken repeatedly with 0 or more occurrence. So the self loop is taken for Q1, where 0 can occur or without occurrence it can lead. That is called as the closure of A. So these are the some examples with the properties how the regular expression can be converted to finite automata. Then comes the next one, the types of the finite automata. We have two types of finite state automata called as the non-deterministic finite state automata and deterministic finite state automata. When we talk about this non-deterministic, the name itself implies that it is non-determinable. That means for same input symbol, we may have more than one transition from the same state. So that is called as non-deterministic. So for an input symbol from state 1, we can have multiple transitions to different states. So we cannot determine which transition will lead to the final state. So this is called as non-deterministic finite automata. And coming to the deterministic finite automata, it is very well determined in a such a way, on one input symbol from a state we will have only one transition that leads to one end state. So obviously there is no confusion of taking the transitions. So the deterministic finite automata will provide you the feasible solution of on any input symbol. So here we are having several examples given here: non-deterministic finite automata and deterministic finite automata. And comparatively, non-deterministic or finite automata will have several states where we have multiple transitions, but on deterministic finite automata will have reduced number of states with finite transitions.